Hello and welcome to the ENG 4392, your elective class, which is Smart Grids Systems. This class would also cover microgrids and a little bit of renewable energies as well. My name is Behnam Askarian, and this course would provide a comprehensive detail on smart grids. We will learn about the analysis and operation of the traditional power grid, the new challenges and the emerging technologies and assets that make the dumb grid become smart. It's mainly focused on the grid side, this class, rather than the device side. And it's focused on the electrical systems rather than the communication systems because the thing that makes actually a dumb grid a smart grid is the connection and the communication between uh, the the load and the source and the generation and inside the grid. And the emphasis is on grid and smart grid operation, energy analysis, management, control, architecture, and also software systems. Now, the objects of this system, this course, the course objectives would be: first, we would study a little bit about traditional power grids, the concepts, operations, and reliability, energy markets, and our main focus would be on next generation smart grids to understand multiple smart grid features and technologies, and to dive deep into the smart grid features. And we would hopefully do a class project on that as well, which is going to be a research project. I will explain more about the class project. It will be an article that you need, a few articles that you need to read, journal papers, and write a report on those papers. Now, the course syllabus, as I mentioned in the previous in the introduction of the class as well, is going to be power flow, sensitivity factors, economic dispatch, and then in the third week we're going to have unit commitment, states estimation, energy markets, wide area monitoring systems, false data injection, cyber attack and detection, renewable energy sources, energy storage, distributed energy resources, microgrids, and advanced metering infrastructure, demand side management, and flexible transmission. Now, before we start, we have to do a quick overview of a power system and to understand fully what is a power system. So, a power system is an interconnected network, or sometimes we also give it different names as well, such as the electric grid, power grid, um, electric network, electric power systems, electric power grid, electricity grid, etc. And it is for delivering electricity from the producer, power plants, generators, solar farms, wind turbines, to the consumers, which could be residential house, industrials, and so on. The National Academy of Engineers, NAE, uh, cites that electric power grid is the world's largest machine and the greatest engineering achievement of the 20th century. So most machines what we have are nowadays are separated. Smart grid power grid in general is an interconnected system. We have standards. It has to maintain a certain voltage, frequency, and synchronizing all of that is a huge task, and maintaining that as well. Now, power system, as mentioned, is very complex, and it contains hundreds of thousands of components. It has large scale network connecting different areas and with different voltage levels. For example, in the transmission or the generation side, we have step up, step down voltages and transformers that transform different voltage levels and match them. We have AC circuits, including the resistors, inductors, and capacitors. We have the power flows, which are nonlinear and non-convex. And we also have the problem of instantaneous power balancing as well that we have to solve. Now, most of you are already familiar with power systems. You had the power system analysis class, but this course is mainly focused on smart grids. So what makes a grid smart? The most important feature of a smart grid, it's it is its ability of having a two-way communication system between the customer or consumer and provider. Meaning, so the traditional grids, it was a one-way connection, meaning the power would just flow from the generator to the producer, and the producer didn't have any idea how much power the consumer is consuming at each time. But now with smart meters and advanced metering infrastructure, the the production side and the grid would know exactly how much power in real time the consumer is consuming. And for example, if during a peak hour or in a peak of summer they want to boost production, they will get that data from the meters and boost production in the generation side. Now, these smart grids are very flexible. They have flexibility in network topology and parameters. They demand side management. They have the peak curtailment, the integration of renewable energy sources, which is an important part of these smart grids, integration of distributed energy resources or DERs, and distributed control systems as well. The technologies and assets that integrate clean and renewable energy sources enhance system reliability, resilience, and cybersecurity, improve energy efficiency, or provide consumers more options are all considered part of a smart grid. Now, a smart grid, as mentioned, is more complex than a regular grid. We have the integration of utility scale renewable power plants, their availability and variable generation. And one example, if I don't know if you're familiar with the dot curve. So a famous curve that we have is called a dot curve. And this actually is the average consumption that we have in a household. And this actually continues. And I think to make it a little, let me erase this and make it a little. So the dot curve is the power consumption in a usual household at the morning when everyone wakes up. So this is around 7 a.m. to 10 a.m. Everyone wakes up, they turn on their coffee and toasters and so on, coffee machines and toasters and so on. And they go to work during the day, and at noon we have the drop in the demand because everyone has work at school or so on. And in the afternoon again, everyone comes back. They turn on their washer, dryer, and so on, and turn on the lights, and we have another peak. But the problem with renewable energy, especially solar, is the peak of production is actually the opposite of this. So usually in the morning we have a low production. So the red one shows the solar power production, and around noon we have the peak. So we have a mismatch between the production and also the consumption. So a smart grid must be able to manage that, shift that with different techniques. For example, using storage systems, we can store the excess energy during the day and shift that during the peak demand, or using a smart meter, we can encourage people to do some of their turn on some of their appliances, or for example to charge their EV during the off-peak hours, which are during the noon or middle at the night. If we have another source of renewable like wind, again after midnight there is not a lot of consumption, everyone is asleep, so it's the best time to actually charge your uh, EV overnight. Now, another complexity, we have the integration of distributed energy resources, it's widespread among the networks, intermittent renewables, and we have the behind the meter distributed energy resources as well. Again, with the rise of these solar panels, and in some parts of the country actually have become mandatory, such as California and Hawaii, parts of Hawaii. So a lot of these homes now have these solar panels, and a smart grid, usually they are given a two-way smart meter, and the two-way smart meter, uh, as its name states, can work in both directions, meaning you would buy your power from the grid during the day, for example, during the night, and then you can sell that back to the grid during the off-peak hours when you have the excess energy. So imagine you have a solar panel on your roof. At noon, when you're at work, you are generating more energy than you're consuming. You would sell that to the grid, and during the night, when you need that power, you're gonna buy that power back. So a smart meter, two-way meter, and the problem again, it's with these being widespread. And imagine you have 1,000 generators, 1,000 homes in a neighborhood, and some of them don't generate energy at the same time. Some have more consumption, some have less. So being able to integrate this into the grid is going to be a very difficult task. Sometimes you have to just cut the power and stop buying when, and this is the actual problem in California right now, is that they're generating too much power that the state doesn't know what to do with during the day. So they just have to, they have stopped buying that power, excess power, and it's caused a lot of problems in the grid. Now, the other problem is going to be challenge is going to be integration of electric vehicles, the frequent fast battery charging, roaming feature, electric vehicles again. Um, Sometimes you need to do a fast charging, so it requires a lot of power. So, for example, if you want to charge a 100 kilowatt hour battery and you want to do it in half an hour or an hour, it's like consuming 10 homes power uh, in 1 hour. And it's going to put a lot of stress in the home. And the change electric demand profile geographically and temporarily. And another problem for these again is going to be that um, if you're in a state that is colder compared to the part that is warmer, you're going to have different demands with the EV. Some EVs now have two-way systems, meaning you can charge and use that as a backup and a storage unit to run your appliances at home as well. How to be able to integrate that is going to be a problem, and it affects the demand as well. Now, more power electronic devices connected to the grid. We would have a flexible AC transmission system, or FACTS, or FACTS devices. And other challenges are going to be the demand response, smart meters, and many other new features and changes that we see in smart grids. Um, and nowadays, there's been a lot of integration from AI as well. So I've included several links that I think it's going to be a great resource. I'm not going to play them all. I'm going to just play one of them, but I will highly recommend that you watch all these videos. It's going to give you a good picture of what a smart grid is. And I would encourage you to watch the other videos as well. They are very, um, very good videos. You get a lot of information for them. Now, some elements of the power system and the grid, which, as mentioned, it's a network of interconnected elements that are used to generate, transmit, and consume electric power, are as follows. We have the generators, loads, transmission lines, transformers, phase shifters, breakers, shunts, HVDCs, and so on. Now, energy power system contains of three major components. We have the power generation, we have the transmission system or the electric network, which are high voltage transmission networks and low voltage distribution networks, and finally we have the electricity consumption. That could be your home or a factory. Now, this diagram shows this power system and the grid, entire grid, from generation to distribution and consumption. As you can see here, the red shows the generation, the blue is the transmission, and the uh, green is distribution, and the black is the consumer part, the customer. So generation could be a centralized generation like a nuclear or a gas power plant. And then immediately at the generation side, we have the step up transformer. The reason we want to minimize loss in the system, so we have to increase the voltage and decrease the current. The transmission lines are the 765, 500, 345, 230, and 138 kilovolts. And we have different systems in different part of the countries, and if different countries have different standards as well. The transmission customer is 138 kilovolt or 230 kilovolt. Then at a city, for example, we have the substation step down transformer that reduces that voltage. For sub transmission customers, which is around 26 kilovolt to 69 kilovolt, or for primary customers, 13 kilovolt and 4 kilovolt, or secondary customers, which are the homes, which are the 120 volt or the 240 volts two phase that you use in your dryers and also your ovens or electric cooktop. Now, this shows another side of that same graph. And here we can see that the high voltage transmission subsystem is a meshed network, and the low voltage distribution system is the radial network, or it has a tree structure. So if in the exam we ask which one has a mesh network, the high voltage, and the low voltage has a tree structure. This is another graph showing the power system. You can see the generation, the distribution, the power transformer, transmission substation, distribution substation, and it could be used in the homes or different industries. Now, this is a power system diagram for UK, and for UK and Europe, they use different voltage. They do use a different frequency. In the US, we have the 60 hertz. Other parts of the world, they have 50 hertz. And for the customer part, for us, it's 120 volts. For them, it's 220 volts. Now you can see it's the same. We have the high voltage transmission of 400 kilovolts or the 265 kilovolt. Then we have the lower voltage distribution of 132 kilovolt. So this is step up voltage. Then we have the step down voltage, another step down voltage, and then the final step down voltage for heavy industry and for homes and light to medium industries. Now, this shows a power grid with different power generations. So we have the solar, wind, a gas power plant, nuclear power plant, hydroelectric power plants, and small generation power plants as well. And here you can see this is a typical layout for Germany and other European systems, you can see that a typical nuclear power plant is around 600 to 1700 megawatts, a coal power plant around 600 megawatts, a medium-sized power plant is 150 megawatts, a hydropower plant could be 2,000 gigawatts. I'm sorry, yes, around 22,000 megawatts, or 22 gigawatts. And you can see the different distribution and the transformers and the connections in the grid. Now, some numbers for the U.S. power systems. The transmission lines are around more than 390,000 miles. High voltage lines are around 200,000 miles. We have over 8,000 power plants, over 300,000 electric utilities, over 145 million customers. The electric power system infrastructure asset is about around $1 trillion. The transmission infrastructure investment is over $10 billion per year. And imagine if we want to rebuild the system and build a brand new smart grid. You can see how expensive would that be. It took around 100 years to build all these, and most of them are needs constant upgrade and reinvestment. So it takes a long time to go from this to a complete smart grid. Now, some numbers of the U.S. power systems, the electricity, and this is from 2017. So the electricity consumption was 3.82 trillion kilowatts. The electricity generation was 4.03 trillion kilowatts. Wind power was 254 billion kilowatt hours, 8% of the operation electric generation capacity. And Texas wind accounted for 25% of U.S. wind. Fuel consumption per day for coal, it was 1,818,000 tons. Petroleum was 106,000 barrels, and natural gas was 25,000 million cubic feet. So installed electricity generation was 1 terawatt. And currently in the latest data that I could find from 2024, the electric consumption jumped to 3.98 trillion kilowatt hours. Electricity generation went up to 4.31 kilowatt hours. Wind power generation is 452 billion kilowatt hours. Again, 12% of the operating electric generation capacity. Wind share of total net summer capacity was about 12% in 24. Texas wind accounts now for 28% of U.S. wind capacity. The fuel consumption per day for electricity generation, daily annual average, daily average annually for coal, it was 1,000 tons per day. So coal went from 1,800 down to 1,000. This is the only one that reduced. Petroleum went for 106,000 barrels to 80,000 barrels per day. Natural gas increased substantially from 25,000 to 37,000, so 12,000 million cubic feet more per day. So coal and petroleum are being replaced with natural gas and also nuclear and renewable. Installed electricity generation capacity in 2024 was 1,230 gigawatts. So from 1,070 gigawatts or 1 terawatts to 1.23 terawatts. Now that's it for today's class. If you have any questions, just please email me. Immediately after the class, I would upload, if the class is uploaded, I would upload the quiz, and you would have 1 week to take the quiz. Thank you so much and have a great weekend.